So sometimes when we are trying to find an area under a curve, we can't use integration. Or sometimes we can use integration, but we don't want to. And so we want to find a rough area, just roughly, what is it? So it's not going to be exact like integration, but it's going to give us an idea, and it means that we can do it when we can't use integration. So obviously with this one we can use integration, so we can say, well, this is the integral from 2 to 3, and it is x to the half dx, which is increase the half to 3 over 2, turn it upside down, put the 3 in first, 2/3, 3 to the 3 over 2, and then put the 2 in, 2/3, 2 to the 3 over 2, and this isn't going to be very nice in terms of decimals, but I can keep it nice in terms of exact surds. So I've got root 3 cubed minus 2/3 root 2 cubed. Now root 3 cubed is root 3 times root 3 times root 3, which is 3 root 3. That 3 cancels that 3, so I end up just with 2 root 3. And then I've got 2 times, I've got root 2 root 2 root 2, which is 2 root 2.
Yeah.
So that gives me overall that. So that's the actual nice, lovely answer. But what we're going to see is how to use a method to approximate it. And we do this by making trapezia even. So we split it up. I've split it up into 4. So this is going to be the point 2.25, and this is 2.5, and this is 2.75. And what I'm going to do is individually work out the areas of these trapezia, which aren't exactly the curve, but roughly, and then add them up. So we're going to need a calculator for this. So A, this is A. A is 0.25 along the bottom. Could you please put the number 2 into the function root x?
It's going to be root 2, isn't it?
Well, it's going to be root 2, but this is an approximation, so I'll just have it to 3 decimal places. That will do.
1.414.
Okay. And what about when you put 2.25 in? What height do we get? So we put 2.25 into this function to get the height.
1.5.
Is that to 3 decimal places? Okay, so that's A. And then I'm going to look at B. So, this is 0.25 across, isn't it?
Yeah.
I was just about to say to you, can you put 2.25 in to find the height? But I've just realised we've already done that. What about when you put 2.5 into the function to find this right-hand side of B, right-hand?
1.581.
581, okay, and then 2 to go. So again, I know this left-hand side now, don't I? And the bottom is still 0.25, they all are. What about this right-hand side?
1.658.
Okay, and last one, D, again, 0.25 there. Again, I already know the left-hand side, because it's the same. Right-hand side?
1.732.
And you got that by putting 3 into the graph root x. Okay, so the area of a trapezium is, we add up the parallel bits, 1.414 add 1.5, divide by 2, and times by the distance between them. And so that's that one. And then this one will be 1.5 add 1.581 over 2, again, times 0.25. And then this one will be 0.25 times 1.581 add 1.658 all over 2. And this one will be 0.25 times 1.658 add 1.732 all over 2. Agree? Okay, so we can add these up individually, can't we? But what I'm thinking is that it might be nice to pull out a common factor of 0.25, and in fact, can we pull out a common factor of 2 of a half as well?
Yeah.
Because everything's being divided by 2, isn't it? So I think what I'm going to do is pull out 0.25 divided by 2. Okay?
Yeah.
And then what am I left with? 1.414 add 1.5 add 1.5 add 1.581 add 1.581 add 1.658, add 1.658, add 1.732. Is that right? Okay, now I've got two of those.
And two of those.
And two of those, which actually makes sense because I found it as the right-hand side of A here, and then as the left-hand side of B here.
Yeah.
But actually that's just the same thing. And similarly here twice, and similarly here twice. But obviously I've only got one of those and one of those, which is that number there and that number there. So actually I could simplify this a bit further and have 0.25 over 2 and have 1.414 and what was the one on the end? 1.732.
Yeah.
And then I've got two lots of 1.5 add 1.581 add 1.658.
Which is a much nicer thing to stick in
Yeah,
the calculator
absolutely.
than all of those horrible sums.
Really, really important. These, we've got brackets inside brackets, so I'm deliberately using a big square one here, and this really does help avoid errors to use a big square one and then little ones inside. Okay, so at this point we can add it up. Another go. So it's maybe start with the thingy.
1.581 at
658.
1.658.
Then times it by 2.
Times by 2.
Then add on 1 point,
414 at 1.732.
and then times that by 0.25, and then divide by 2. What do we get?
1.578.
1.578. Now we happen to know the exact area, don't we? Because we worked it out. So the exact area is 2 root 3 minus 4/3 root 2. 2 root 3 minus 4/3 root 2.
Conveniently, 1.57848.
So we're really close with our approximation. I mean, to 3 decimal places, it's spot on. If we'd used more trapezia, it would be even better. So if we'd, instead of using 4, we'd use 8, for example,
Yeah.
or even 16, you know, then the more we use, the better it will be. But even 4 is quite accurate. So let's have a think what we're doing in general when we do this. We've got a random function, and we're going to work out the area of all of these trapezia, A, B, C, D, E, F, G, H, I, J, K, blah, 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 up to Z, you know, however many you've chosen to do. And for each one, we've got the same height, well, we call it a height, but across the bottom, for the trapezia. So every single trapezia is going to be a half, and it will be, sorry, not half, I keep using the other form of the formula, H. It will be H, yeah? So every single one is going to look like this.
Because it's the formula for the trapezia.
Yeah, and because they're all the same distance across.
Yeah.
All of them, they're all
Yeah.
the same. So that's the same as we had, so I can pull out this common factor of H, of the formula, and H is that distance across, and I can also pull out the half.
Yeah.
So I'm going to be able to pull out the H over 2 deliberately. Okay. Then I'm going to work out this height. That goes there. I'll call that. I'll call it y0. Yeah. They're all y values, all of these, and then you've got the first one, the second one. So actually, I'll just call it first. This is the first y height, and then the second y height.
Yeah.
And then that would be, this bit would be the area of the first trapezia.
Okay.
Then I'd have the second and the third.
Yeah.
Then I'd have the third and the fourth.
Yeah.
And then all the way to the end, I'd have the last and the second to last. And that's all these y values which we get by sticking the corresponding x value into the function. So when we come to add it up, we'll have the first plus the second plus the second plus the third plus the third plus plus the second to last twice, and then finally just the last. And that would be what we'd be adding up.
Yeah.
Which obviously it would be a lot nicer to write it like this. H over 2, and this is the formula we'd use, first y value plus the last y value plus 2 of all the other y values. I mean, I know I'm not writing it using nice maths notation, but there's no need, to be honest. I think it just overcomplicates it.
Mm-hmm.
So, we're going to need to know what is h, and h is the distance at the bottom.
Yeah.
So it's from one x value to the next x value. It's all of these numbers. How far is it across there?
Yeah.
The first y is this height here.
Yeah.
The last y is this height here. So we get the first one by putting this into the function. We get the last one by putting this into the function. And then all the other y's are all these ones, which you get by putting the other x's into the function. And then you stick it all in the formula. Should we have a go?
Let's have a go.
Okay, so we've got the integral, we're just approximating it. And we're going from 0 to 2. So the picture, I don't know what this function looks like, but something like this. And we're splitting it up into 4 different intervals.
Mm-hmm.
So this is the 0.5, this is the 1, this is the 1.5, and that's what these numbers here are.
Yeah.
So these numbers across here represent those x values, which means that we can see straight away that our h is going to be this distance across here. This is what h is, which is 0.5, yeah. So you can always spot the h really easily by, I'll just write the formula down and then we can sub into it. Being a bit lazy there with the formula, but you get the idea. So we can see straight away that h is 0.5. Okay, so now we need the heights. This is going to be the first height. This is going to be the last height, that one, and then these in the middle of the other heights. So how do we get those other heights, or all of the heights?
We need to put the x value that we have, so, and we can hold around that, the x values that we have into that equation.
Yep, that's it.
Yeah.
Yep.
So that's root 3, which is...
Yeah, so if we put 0 in as x, we get root 3, which is 1.732. And what are we putting in now?
0.5.
So it's 2 times 0.5, add 3, square rooted. Is that right? 2, yes. Okay, and then what we do? 1. So that's root 5?
Yeah.
2.236.
Yep, 1.5.
Okay, 1.5 times 2 plus 3 square rooted is 2.49, no, sorry, 2.449. Okay?
And then 2 is the last one.
So that's 2 times 2 is 4, and 3 is 7, root 7 is 2.646.
Okay, so our first one then is 1.732.
Yep.
Our last one is 2.696.
Yep.
And then we want 2 lots of 2 plus 2.236 plus 2.449.
Yep. Which is times 2 equals plus 1.732 plus 2.696 times 0.5 divided by 2. I make it 4.4495. Okay. Now, it seems fairly straightforward this, but we might have gone wrong.
Yeah.
And I can't check it by integrating because I can't integrate that function until C4. So when you learn C4, you learn to integrate that function, but at the moment we can't. But of course, I have a calculator that will integrate it. So I'm going to type in the integral into my calculator of the square root of 2x add 3. And that's going from 0 to 2. From 0 to 2. So what I'm getting from my calculator is an exact value of that area, and the exact value is 4.4414, blah, blah, blah. So, not that bad. I mean, 2 decimal places, it's enough. We only broke it up into 4 intervals. It's enough to convince me we haven't gone wrong.
Definitely, yeah.
I mean, if we'd got 12.7,
we'd have issues.
yeah, we know we've gone wrong, but to 1 decimal place it's correct. So it's not bad, I think.